You may wonder what the special relativity is. Let's have an introduction. In 1905, Albert Einstein, by introducing this very stunning theory, proved that space and time, despite of the classical belief, are dependent on each other and they are relative to you. Classical mechanics believes that space and time are independent of each other and they are absolute, but Einstein said no, they are dependent on each other and they are relative to you. What do you mean by that? Let's have an example. Here we have a ground observer and a spaceship. This is a relativistic spaceship because it's moving really fast. 0.6 c. It's 60% of the speed of light. Fast object that's going to be a relativistic case actually must move approximately faster than 10% of the speed of light. So larger than 0.1 c is considered as a relativistic case. However, this spaceship starts its journey, goes for a few seconds. What do you mean by few seconds? Oh, that's very important. The ground observer will measure the total time of this journey 10 seconds. But if you ask the passengers of the spaceship, they will confirm that this is not correct. It is 8 seconds. Oh, it's very crazy. How come? Do they have a different measurement of this on the same journey? Yes, they do. Do we have different time scales for the same event? Yes, we do. Do we have different realities? Yes, we do. Reality is dependent on you. Oh, the length of the journey as measured by the ground observer seems to be 1.8 gigameter. Means that it's 1.8 10 to 9 meter. But according to the passengers of the spaceship, it is shorter. 1.44 gigameter. It's 1.44 10 to 9 meter. Oh, it's again another strange case. The distance traveled by this spaceship is relative. The ground observer and the passengers of the spaceship, the moving passengers, will have different measurement on the length. Yes, this is why we need special relativity for high-speed objects. Another strange case. We have a couple of cars, a yellow one moving at a speed of 30 meters per second leftward and the blue one moving at a speed of 10 meters per second rightward. Okay. I asked the driver of the yellow car how fast the blue car is. He will say, okay, in every second I'm moving leftward for 30 meters and at the same time the blue car will travel for 10 meters. So we are approaching each other for 40 meters in every second. So the relative speed, according to classical mechanics, what the Galileo said, what the Newton said, is 40 meters per second. Okay, let's go to the fast object according to relativistic mechanics. In Einsteinian relativity, we can consider very fast object like this. This is a spaceship moving at a speed of 0.8 c. It's really fast. Okay, and then we can turn on a flashlight. It sends a light signal toward the spaceship. If you ask the passengers of the spaceship how fast the light is coming to you, according to classical mechanics, okay, what did we do there? We said, okay, 10 plus 30 is 40. So let's do it here. C plus 0.8 c, so it's 1.8 c. But it's not correct, unfortunately. The speed of light, as Einstein proved, it is absolute, it is not relative. So it's c. Whoa, what happened to this 0.8 c? I will explain it later. Now keep in mind that the speed of light is absolute, it is not relative. Regardless of who you are, how fast you are moving, to which direction you are moving, always you will measure the speed of light as c. What about another spaceship which is approaching to the first one at the same speed? If you ask the passengers of this spaceship how fast the other one is moving toward you, what do they say? The Galilean mechanics says, okay, 0.8 plus 0.8, so it is 1.6 c. But unfortunately, this is again incorrect. We will introduce a formula for that, and that Einstein explained it, and this is 0.98 c. Nothing can go, even in relative speed, faster than the speed of light. So the speed limit for everything, even for relative speed, is c. It's going to be 0.98 c, but what the formula is, in upcoming lessons we will learn them. So for a classical observer, the space sounds like this. It has the same scale in both directions, vertical and horizontal, okay? For a relativistic traveler, the space in the direction of motion is getting contracted. You see, vertically it's not affected. The scale of the space is the same in vertical direction, but in horizontal direction, the direction of motion, the length is getting contracted. This is called the contraction of length. Time is also affected because of that relative speed. You measure the time on your clock at a specific pace, according to the clock which is at rest relative to you. But when you see the clock in the spaceship, you will see a slower pace. It's going slower. So relative speed not only affects space, but also affects time. This is why Einstein said space and time are not independent of each other. And so he preferred using the combined expression of space-time instead of space and time. Although Einstein and Newton had different perspectives on the physical world, but they had something in common. The laws of physics, both believed that, are the same in all inertial frames of reference. If you consider the time and space, no, they have different perspective. Newton believed that space and time are absolute and independent of each other. Still, for objects moving not that fast, it is correct. But for relativistic objects, Einstein believed that space and time are getting to be relative and dependent on each other. More than that, Einstein confirmed that and emphasized that the speed of light relative to any observer in an inertial frame is independent of the motion of the source of light relative to the inertial observer. Means that no matter how fast you are moving, to which direction you are moving, the speed of light is always absolute and c relative to you. Are they really fighting with each other, Einstein and Newton? No. No, actually, they have different fields of work. If you are moving not that fast, slower than 10% of the speed of light, Newtonian mechanics is okay. You can use space and time independent of each other, as probably you have learned it, and there's no problem. But faster than that, let's learn relativistic mechanics, in which Einstein proposed space-time instead of space and time. Okay, thank you for watching this video, and in the upcoming video I will introduce inertial reference frame and we will proceed and delve into the relativistic mechanics. See you soon.